the example that I want to use to develop this idea is a set of physical changes. But it also applies to chemical changes, reactant side to product side. You will have energy going into the reactants to effect a generation of products. Same concept. But this is called the heating curve. And it is I'm presenting it and as a function of a problem that's couched in these terms. Okay, calculate the total amount of heat energy required to convert 10 grams of ice at a minus 10 degrees Celsius to 10 grams of steam at 110 degrees Celsius. Now you need some constants in here in order to do this, and they're called specific heats. Okay, and they are C values for ice. I'm going to put salt, well, no, I better put ice. Is 0.50 calories per gram degree Celsius. And specific heat of water is 1.0000 calorie per gram degree Celsius, and the specific heat of steam, water gas, is 0.48 calorie per gram degree Celsius. So those are constants you will use as we go through this. The other constants that you'll use are phase transition constants. A delta HF FZN is not the heat of formation, it's heat of fusion. I'll define these. And this has to do with melting. And then you have a delta H of vaporization. And of course, that's kind of self-defining, self-explanatory, and that's evaporation. Also, same number for boiling. Okay, well, specifically, the delta H of fusion is 80 calories per gram of ice. And the heat of vaporization is 540 calories per gram. So this is more of a classic type problem that I use every semester to teach this concept of energy flow and how to calculate it in problems you're going to see, and in many cases in real life. Okay, so we're going to convert 10 grams of ice at a minus 10 degrees Celsius to 10 grams of steam at 110 degrees Celsius. The heating curve that is generated from this contains 5 segments. Okay? In the gas phase as steam. Now, draw a vertical like this, and this is going to be temperature. In here, right here. Now we're going to start with our ice at a minus 10 degrees Celsius. And we've got to heat that to the melting point. Now, horizontally, we have energy, heat, in, if you're going that way. If you're going this way, we're taking energy out. In that context. So in order for us to melt our 10 grams of ice solid, we have to add energy to bring it up to 0 degrees as the melting point. The next section is 2 phases or multiple phases in contact. When multiple phases are in contact, even though you're adding energy to the system or taking energy out of the system, there experiences no temperature change. This can be demonstrated in the lab many times. So while we have 10 grams of ice and I want to melt it, there will be no temperature change. Yes, we're putting energy in, but this is the solid-liquid interface. There are 2 phases in that segment. No temperature change is occurring. Now, once all of the ice has melted, everything's liquid water now, temperature change can be effective again, and it will. To boil it, you have to raise the temperature to boiling point. Of course, that's 100 degrees C right there. And this is our liquid being raised to the boiling point. Once the liquid is at the boiling point, it's now ready to go into the gas phase, so that means we have gas and liquid, 2 phases in contact now. So again, while boiling is taking place, no temperature change occurs. If you take a thermometer and put it into a pan of water while you're trying to boil it, you'll notice the water will continue to boil, but your temperature will reach 100 degrees and stay there. Okay? This is your liquid-gas interface right there. And then once all of the liquid has been evaporated to the gas phase, then you can heat it on up to the 110 degree C objective, and that is your gas phase. Okay? So there are 5 segments in here that involve energy flow. And each segment has a specific equation that is used to calculate energy change in that segment. Now you notice three of the segments in here have a, diagonal or increasing due to changing temperatures. And then you have two segments in here that don't change. Well, the segments that do change in terms of energy are defined by Q equals mc delta T, where m is the mass undergoing the change, c is that constants that we talked about, the specific heat constants up here, okay, and the change in temperature from start point to where it goes into its phase change. So you see those slopes or temperature change, Brain says use mc delta T. In the other regions, there is no temperature change. Notice the flat part. The energy involved with that is simply the mass undergoing transition times the phase transition constant. Whether it's heat of fusion if you're melting, heat of vaporization. Look at some of you and you look like y'all have had this stuff about 1,000 times already. Enjoy the review, okay? All right. So when we calculate as indicated in our problem, calculate the total heat energy required to go from a minus 10 degrees up to 110 degrees, we make 5 calculations. One for the solid, we'll have a Q for the solid, we'll have a Q for the solid liquid, we'll have an energy for the liquid, we'll have a energy change for the liquid gas, and a Q value for the gas phase. So we calculate each one based upon the equation that defines that change. So our first Q value is, of course, the warming of the solid up to, and it involves a temperature change. Since it involves a temperature change, mc delta T is the equation of choice. Now when we get into the solid liquid, that will be the second one, the solid liquid, the melting. We will use the phase transition equation, which is simply m times delta H of fusion. Like that. So in the first case, we have 10 grams times 0.50 calories per gram degree Celsius. This could be, of course, done in joules if you wanted to. Calories is a lot simpler than the presentation. And we have a 10 degree Celsius change. And if you'll notice, the grams will cancel. The units will cancel of temperature, and we're left with energy units only. And so that is, and I'll bring it out here, 50 calories. Okay, then we repeat for the next section, the solid liquid section, and we again are melting 10 grams, and we pick up the heat, the phase transition constant, which is published in the problem, 80 calories per gram. And so that'd be 80 calories per gram. Notice in this phase transition constant, there's no temperature term, because, of course, there is no change in temperature during that phase change period. And so we have 800 calories. And so we continue that for the remaining regions. Now that we have melted all of our ice, we're ready to heat it to 100 degrees. So that's pure liquid phase. It involves a temperature change, so it's mc delta T again. And so we have 10 grams of water now. That 1.00 calories per gram degree C. times 100 degrees C is the temperature change this time. So we have 1,000 calories just in that region right there. Everybody still with me? Then we continue with the liquid gas. Fixing to lose it a little bit here. Liquid to the gas phase. This is a two-phase in contact, a phase transition. Mass times, this time it's vaporization. VPZ, VAP, but 10 grams times 540 calories per gram, and of course that's 5,400 calories. Would somebody run a total on that for me in their calculator while I'm doing this? I appreciate it. Okay. And then finally, the steam or the gas phase, if I'm still on the board, is a temperature change region up here. And so that's an MC delta T for the 10 grams of gas now, 0.48 calories per gram degree C times 10 degrees C. Of course, we could have chosen higher temperatures if you wanted to, but I just kind of keep it simple there. And that's, of course, 48 calories. And so we've taken each one and computed the amount of energy necessary to make the change. So to emphasize this in a different context, this is 50 calories right there, and not drawn to scale, okay? And then it's 800 calories. And 1,000 calories. And then, of course, we have 5,400 calories, and then up to the steam point 48 calories right there. Now, the total would simply be the sum of those. That's all it is. Anybody run this out for me? 1998. Okay. Times 4.184 joules per calorie, of course, will carry you to joules if you so needed to, for whatever reason, arbitrary reason. Uh, 305.35 joules, which is 3.05 times 10 to the third, let's see, 1, 2, 3, or fourth, well, third joules, and you can divide by 1,000, and 30.5 kilojoules. It's a matter of how you wish to, or whatever the problem's asking you for, or whatever the case may be. Okay?